Hello students, welcome back. We went through a diagonalization problem, but without any proof. So we're going to do some proof here. Let's go back to section 2. This is the theorem, the root of everything. We can find appropriate diagonal matrix D given by all the eigenvalues if there is a basis that consists of eigenvectors, which we call eigenbasis, then the diagonal matrix lambda 1, lambda 2, all the way over to lambda n like this, can be written as T inverse AT, where T, the transition matrix, is given by the coordinate expressions of eigenvectors. First, second, and so on forth. Now, if you have that transition matrix and the diagonal matrix, then you can calculate any power. And one such example was right over here. You can find the eigenvalue by characteristic equation. Okay, and for each eigenvalue, you can find eigenvector through systems of linear equations. 2, -3, 4, 1, -1, 1, 1, -2, 2. Check the linear independence. I'll leave those to you. And then consequently, we have this diagonalization. Transition matrix is 2, -3, 4, first column, 1, -1, 1, second column, and 1, -2, 2, the third column. So the diagonal matrix can be written as T inverse AT, or equivalently speaking, A can be written as D, it's down here. A can be written as TD T inverse, and using this, you can express any power, any kth power of A using T d to the k power T inverse. So A to the k power is T d to the k power T inverse. So we have any power series expansion like T, whatever power, and then T inverse. We can consider other kind of power series expansion as well, like sine or cosines, but what's the point? The most important is exponential. So let's do just exponential, and that's hard enough. And here we go. All you have to do is T e to the d T inverse. That's it. T e to the d T inverse. Look at all these. Exponential of eigenvalues in the diagonal. So that was one heck of a long problem. And we went through one example problem like that. And if I write an exam problem like this, then please expect a long problem, which is chopped up in several different places, like find eigenvectors. Find eigenvalues first, part 1. Find eigenvectors, and quite probably I may have to give you the answer so that even if you book down in some kind of computation, then you can retrieve it back. And then exponential computation or any other power series. So they're all coming from this diagonalization theorem. And now let's begin the proof. Ready? Okay, here we go. This is something we did at the end of module 5, change of basis theorem, but let's revisit this issue. Let's begin with a vector space V, and let's consider two bases, V1, V2, V3, all the way over to Vn, which will typically be the standard basis vectors, and W1, W2, W3, all the way over to Wn, which will be the eigenvectors, bases given by eigenvectors. That's our goal. In general, V1 through Vn generate entire vector space V, so all the vectors here can be written as a linear combination. In particular, W1 can be written as a linear combination like this. W2 can be written as a linear combination like the second line, and so on and so forth. And in the end, Wn can be written as a linear combination of V1 through Vn. Now, how do you use this? For arbitrary vector V, you can use first basis V1 through Vn to get the coordinate expression x1 through xn, and also you can use the second basis W1 through Wn to get the coordinate expression y1 through yn. And here's a visualization. Here, the vector v is 4, 3. Position vector here, starting from the origin, going to 4, 3. And v1 and v2 are standard basis vectors, as they usually are. And 4 units in v1 direction, and 3 units in v2 direction, and there you go. Now, W1 and W2 are slanted, and what we want is basis given by eigenvector of a certain linear operator, but in this case, we don't have linear operators, so I just made up. So W1 is slanted like this, and in W1 direction, I have to move 1, 2, 3, 4, a little bit less than 5 units in W1 direction, and in W2 direction, I go 1, 2, 3, and about 3.5. A little bit more precisely, 4.87, 3.47, or even more precisely, like this. So we have two different coordinate expressions for the same vector v, and that's because we have two different bases, 4, 3 coming from the standard basis, and then 4.87, 3.47 approximately speaking, coming from slanted bases. As a matter of fact, in this particular case, W1 and W2 are like this. 1, negative 1/3, negative 1/4, 4/3. So linear combination of W1 is like this, and linear combination for W2 is like that, which actually corresponds to the first line and second line of this general situation. And this general case here is for n-dimensional case, and the picture I showed you was 2-dimensional, so we have only 2 vectors and 2 lines. But you can still see the pattern here. So now question here is, what is the relationship between the first coordinate, x1 to xn, and the second coordinate, y1 to yn? The answer is this. X equals to ty, where t is the transition vector obtained by all the coordinate expressions of W1 in the first column and all the coordinate expression of W2 in the second column, and so on. Look at the color coding. W1 is a certain coordinate, and in the previous picture, W1 was 1, negative 1/3. So 1, negative 1/3 goes to the first column. So we are taking columns and columns and columns. Have you done this before? Yes, you have. When you're looking for the matrix associated with a linear map, you took those columns. You found out those image vectors, the coordinates of the image vectors of each basis, and there's columns and columns and columns. That's what you did. And we are doing pretty much the same thing here, and deep down they are connected. And then the answer here is x equal to ty. That's how they are related to each other. Now the proof is rather technical. I'll go through it very, very quickly. If you follow, great. If you don't, that's okay. You can just move on. V can be written as a linear combination with respect to w's like this, y1 w1 plus y2 w2, and so on. And for each w can be written as a linear combination of v through vn. So plug this W1 over here, plug this W2 over there, and so on from here, and then do your computation. You're going to end up with, let's see, W1 is this, and W2 here is that, and so on. And then you can rearrange them, and you're going to get this expression. So this corresponds to x1, that corresponds to x2, and so on. So compare. The result, x1 is this linear combination, x2 is this linear combination, and so on, with respect to y1 through yn. And that happens to be equivalent to this matrix multiplication. x1 is first row, dot product of this column. x2 is second row, dot product of the second column, and so on. Color coding will help. Blue goes to blue, red goes to red, and so on. In the end, what do you get? X equals to ty. That's the conclusion that everybody has to remember. As for the proof, if you follow it, great. Even if you don't follow it, there are too many indices, so I'm not going to impose this kind of things to anybody out of scratch. Next topic, how about the similar matrices? How are they arising? Okay, let V be a vector space with basis V1 through Vn and W1 through Wn, and the transition matrix we just talked about. W1 in first column, W2 in second column, all the way over to Wn in the last column with respect to V's. Let's see, is there something hidden there? Yeah, okay, yes. Coming from the linear combinations, all right. Now, given linear map F from V to V, so it's a linear operator, the matrix A associated with this F under the first basis, this basis, that's matrix A, and matrix B is the same linear map, same linear operator, and matrix representation with respect to the second basis. So same linear map F, but we have two different matrices associated to those, A and B, because we have two different bases. A is with respect to the first basis, V1 through Vn. B is associated to the same matrix, same linear map, but with different bases. Turns out we have T inverse AT, same as before, or kind of like this. So B1 is the first basis, B2 second basis, and so on. We are doing all the columns as usual, all the columns, and then we have T inverse AT. Okay, how do you prove that? Well, okay, let's see. We'll say V star is f of V. Then, with respect to the first basis, V1 through Vn, it'll have coordinate expressions. We'll call it x star. All the x's are for the first coordinate, V1 through Vn. And V, we're going to get x star equals to ax. Likewise, from here, express everything in terms of the second basis, W1 through Wn. Then we're going to get coordinate expressions. Let's call all those as y's, and y star equals to by. So this and that are actually both equivalent to this one in terms of different bases. Okay, and then what's the relationship between x and y? Well, here we go. X equals to ty, as you did in previous theorem. And likewise, x star equals to ty star, as we did in previous theorem. So all I have to do is plug those into these two and do some simplification, and you're going to get the answer. Here we go. The y star is, x star here is equal to ty star. And then that equals ax, but x is ty. So what do you get? Ty star is equal to aty. So flip this t to the other side, and what do you get? Y star is equal to, flip this over to the other side, T inverse AT times Y. But then again, compare that with this. That should be equal to BY. So what do you get? T1 inverse ATY is equal to BY and we have the result. T inverse AT is equal to B. If you could follow, great. Even if you don't, just remember the result. We have this similar result. Okay, now algebra of similar matrices. Okay, any nth power, if A and B are similar, that is, if you have T inverse AT in this form, A to the nth power and B to the nth power have the same, exactly same relation. Excuse me, did I say same? Sorry, similar relation. So how do you do that? Well, B to the nth power, just express those as repeated multiplication and just take associativity. That cancel out. All the middle t's cancel out. They all become identities. So in the end, what we get? T inverse A to the nth power t. Precisely what we wanted. So A and B are similar. That is, B equals to T inverse AT. Then A to the nth power and B to the nth power is similar as well. Same way. Repeat this for all the polynomial expression. Then, well, we have T inverse AT for these two. And then same thing here. Same thing there, all those. And then for i's, T inverse times T is equal to I. So yes, we have the same thing over there as well. So nothing there. If a power series, you can do that because each power, each nth power and b nth power, they are similar as T inverse A to the nth power T, like that. Of course, do they converge? And then does this power series expansion make sense is another question. But for exponential functions, yes, it does. You know, exponential is well defined for negative infinity to infinity. Everybody knows that, right? We did it in calculus too. The interval of convergence for exponential is negative infinity to infinity. So it's okay for exponential. And for a differential equation, we need only exponentials. How about for inverse matrices? All you have to do is flip those inverse of inverse, and that's about it. So what do you mean by A and B are similar? B can be written as T inverse AT, and then flip those over, and then what do you get? TB is equal to AT like this. And then we want inverse matrix. So instead of just taking T inverse, let's take A inverse as well. So take A inverse there, A inverse there. That'll cancel this A out, because that's identity. So what do you get? A inverse TB equals to T. I'm almost there. Almost there. And then take this. Let's see. Yeah, I could have taken B inverse to the other side here, but I decided to move T over here first. Okay, let's do that. Do it that way. Take the T inverse over here, and then got identity matrix. So this times B is I, so that's the inverse matrix of B. In the end, what do you get? We have the same thing, T inverse, A inverse T. Same thing. So any nth power, even for negative integer power, it works out. That completes all the theoretical details for diagonalization. And as for how to use diagonalization, we already did it in previous videos, so let's call it done. And let's do section 3 in the next video. Okay, let's stop here. We don't have time.